Now we're ready for part 2 of this FIRA first day. We've called it the Robotic Revolution, and James SULECKI will be the moderator. Please, James, come here with me. You're Meister Media's Chief Content Officer, and we are very pleased to welcome you.
Well, good morning, everybody. It's very much a pleasure to be here today. It's great to have such an international crowd. I'm from the United States, actually from a city called Cleveland, Ohio, which is the home of LeBron James and the Rock and Roll Hall of Fame. So just to give you a little bit of an idea. Just some opening comments before we get going on this next panel discussion. Thank you. Called the Robotic Revolution. First, I'll back up. For those of you who are not familiar with Meister Media Worldwide, we are a publisher of publications, magazines, and digital products and events specifically for agriculture and horticulture. And these are all of our titles. I oversee all the content for the company on events and digital and print. And I also do something called, I head up something called the Global Precision Initiative. And what this is our own way of advancing not only robotics, but precision agriculture in general, which is really important to us. These are a couple of the things that we also have available. If you're not familiar with our website, precisionag.com, by all means, please go to the site. It'll give you a lot of information, not only in North America, but throughout the world about precision agriculture developments. We also have something called the Precision Ag Institute that does research, education, and advocacy on behalf of precision agriculture and ag technologies. We also do an event, many events for precision agriculture. We have one coming up next month. In fact, we've partnered with here with FIRA, the organizers of FIRA. We've partnered with them on this event, and they are partnering with us on our Vision Conference. And if you're interested in attending this event in Seattle, Washington, it's going to be preceded by a half-day pre-conference on the campus of Microsoft. And we'll be hearing later today from Claudia, who's from Microsoft. If you're, obviously, as a FIRA attendee, you are eligible to get 15% off your registration, and just use this code, or just see me later. But the code is SO15FIRA119. And we hope to see some of you perhaps at the Vision Conference, where we really take a longer-term view of precision agriculture and digital technology. Just a few things about precision adoption. And as I mentioned, we do a lot of research in our markets, and we ask our audiences, where are you in terms of precision agriculture? Do you feel as if optimism is building? And just recently we found out, we did research of many of our audience members, not only in North America, but throughout the world. And what we found that about 57% of all the respondents outside of North America said that they believe that precision agriculture is either already here and is starting to mainstream, or starting to gain real ground in adoption. So this is something we've been watching precision agriculture for about 20, 25 years now, and it's interesting to see it really begin to move now after many years of development. We also ask about which technologies our audiences are especially excited about, and this audience may be interested to know that robotics and automation and mechanization are particularly of interest to them, especially outside of North America. We also recently did a poll of our readers of American Vegetable Grower, which is one of our titles, and we asked them which precision tools do they use currently on their farm. Now, this would be vegetable growers, including the gentleman from Bonaparte in the United States. And interestingly enough, robotics is now beginning to come in as being one of the precision tools that they're using on their farms. And you can see these are all the technologies that they're using. But robotics now at 2% this year, so we're starting to see some movement now within vegetable operations in particular. In fact, if you weren't aware, this story just ran a few weeks ago in the New York Times. So now the consumer media is becoming much more aware of all of the interest in robotics. This is a story titled, "As Immigrant Farm Workers Become More Scarce, Robots Replace Humans." So one of the operations is Taylor Farms in California. Not a grower, but they're a packer, and they have a highly automated a production plant, processing plant that uses robotics and other technologies. So we're really seeing a lot of this is happening throughout the vegetable industry, particularly in California, where just as you have here in Europe, for years you've been dealing with a labor shortage. Now, as you've been hearing in the United States, this is happening as well. And in fact, it's even happening in Mexico as well, which is where the United States has long drawn its labor from. You know, I just thought it was interesting, just to kind of round out my opening comments here. This, I think, is the perception of what robotics are. You know, it's just this robotic arm, and it's going to replace human beings. I mean, there's always been kind of this dystopian view of robotics, when in actuality we know that there's a wide range, as Mark Van Ocht was saying earlier, there's a wide range of sizes and types of robotics. And so it's so exciting to see all these coming to fruition now in greenhouses, in vineyards, and vegetable operations. So it's really exciting, just the excitement to hear in this conference and all the technology that's now actually coming to fruition. So those are just kind of some opening comments from my perspective, just from serving agriculture as I have for about 31 years at Meister Media. And now I'd like to begin our panel discussion. It's going to round out this second session, which of course is called the Robotic Revolution. This is truly an international panel. We have Dr. Noboru Noguchi from Hokkaido University in Japan. He will be followed by Salah SUKKARIEH of University of Sydney in Australia, who's not able to be here. However, he will be joining us via video, and I think it's late evening now in Australia. So this is wonderful that he can join us for questions. And then we'll round out here from Bosch Deepfield Robotics here in Germany from Maurice GOHLKE. So first I'd like to bring up for the first presentation Dr. Noboru Noguchi, and I know he'll tell you a little bit more about himself, but just as some background, he's professor of agricultural robotics at Hokkaido University in Japan. He's professor and director of the Robot Vehicle Lab there. Since 1990, his laboratory has developed more than 15 agricultural robotics. Noguchi has received more than 20 academic awards from major corporations and academic institutions in Japan and internationally. Currently, he's working on a multi-robotic system and the intelligent vision of machines for a mobile agricultural robot. Please join me in welcoming Dr. Noboru Noguchi.
Thank you, James. My name is Noboru Noguchi. Today I'd like to talk about overview of agricultural robot, autonomous robot tractors developed in Japan. I'm working for the universities, Hokkaido University, Japan, and also that I'm in charge of program director, SIP, which is a large-scale R&D program in Japanese government, technology for creating next generation agricultural forests and fisheries, managed by the Cabinet Office, Japan government. Today, I'd like to talk about our achievement of the robot, and also that I introduce our SIP outcome. So, first of all, I'd like to introduce our laboratories. Our laboratory is Vehicle Robotics Laboratories. We are belonging to the Research Faculty of Agriculture, Hokkaido University, Japan. We are engaging ICT and robotics for agriculture. You can see many students and colleagues, and also that we have many robot tractors and vehicles. Actually, the Ministry of Agriculture, Forest and Fisheries, Japan, publish a monthly magazine we call AFF, we call AF. This is features our laboratories in the 2016 as a leader of ICT, robotics for agriculture in Japan. So our laboratory is basically focusing on vehicles. Vehicles including ground vehicles, surface vehicles, aerial vehicles, satellite vehicles. Basically, we have, these vehicles is unmanned or robotics. We have unmanned ground vehicles, more than 15. And then we have also used that surface vehicles, which is boat. Boat is used for the agriculture, in particular the rice paddy field. You can see, this one, this boat is used for power Deepfield to apply the herbicide. Sorry, I can do. Oh, sorry. Okay, and then aerial vehicles. This is very popular. This is a drone and the UAVs. So unfortunately, we don't have a satellite vehicles, but we use information from the satellite vehicles, which is positioning, and also the remote sensing. Today, we're focusing on the ground vehicles. So now, Japan launched agricultural robot this year. We are facing a lot of big challenges of production agricultures, in particular the labor shortages. We are declining core persons, mainly engaged in farming. Now, there are numbers of farmers is only 1.75 million, 50% decrease in last 5 years. And another issue is that the aging of farmers. 65 years old or older accounts for 65% of the farmers. Average age of farmer is already reached to the 67 years old. This is very much problems in production agriculture in Japan. Therefore, Prime Minister Shinzo Abe directed to get robot working in Japanese agriculture by 2018, this year, in the very important meeting, which is Public-Private Dialogue Toward the Futures, held in March 4, 2016. As you know that auto steering is very much popular in the advanced countries, even in the France and then EU countries. Now, okay, you know that Japan, Japanese agriculture machinery manufacturers commercialize that agricultural robot tractors this year. But current technology need to direct visual observation by the human. That means human need to stay near robot working. Okay, that is kind of not good, the efficient way. But the 2020s, we tried to implement a robot system by remote monitors. This is our goals. So why Japan could implement that technology to the real world is that, thanks to the government, we can implement, the manufacturers is that develop robot tractors and then start to sell. Actually, the Ministry of Agriculture and Forestry and Fishery, Japan, established safe security guidelines of robotic agriculture machineries. The purpose of the guideline is to ensure safe operations of an autonomous agriculture vehicles incorporating with the robot technologies. These guidelines also indicate a basic same concept of the safe security, including enforcement of the risk, assessment, and role of the person concerned. This guidelines became more effective in March 2017, last year. Thanks to these guidelines, agricultural machinery, major machinery manufacturers could start to sell this kind of robot with confidence, and also the user, the farmers, can use these robot tractors without worries. That is very good thing, and also that the good news is that insurance companies built new programs, insurance programs for the robot agricultures. That is, okay, we can say that this is an environment for introduce robot is created in Japan this year. So I want to talk about the application of robot tractor associated with the human drive tractors. Today I show that two applications. One is leader-follower type robot use. The leading vehicle is a robot, unmanned vehicles. This is carry out the tillages, make a seedbed. And the following vehicle is a normal tractors, human drive. This is, carry out the planting. So generally, the planting is the most difficult for the works for the using tractors because they're very much difficult to straight run. But in this case, robot tractor can run that very much straight within the 3-5 centimeters. Therefore, and also that robot tractor is make a trail in the soil. Therefore, operator, drivers is easy to follow the trail. And then they make very much precise work. Then also that driver need to be monitored, okay, observes robot tractor work properly. The other application is that separate work. With the human driver tractor, conventional tractor, and then robot tractors. This one, green tractor is a human driver, conventional tractors. Red one is a robot. Robot tractor is at mowing grasses. And then the human tractor in this case is at tilling, subsoiling by driving the tractors. But this one guy is also responsible for ensuring safe operation of the robot. Then, the obvious, one operator can manage 2 machines. Work efficiency become double. This is current technology using robot tractors in Japan. Next step is that, again, remote monitors, remote controls systems. And then this is, goal is that complete by 2020s. Goal of this system implement super labor-saving technologies into agricultural sectors. This is the ideas. So you can see, this is the overview of our systems. Robot control rooms, farm manager sitting in the offices, and then he is managing multiple robot tractors in a different area, different field. Tillages, weeding, spraying, and many robots working in their areas. And then one manager is at the monitor, the all robot work. Core technology is multi-GNSS, such as GPS, and then also GIS. And also this control system is has a function of real-time monitoring of robot, and also automated documentations. So this is ideas we are now developing. So this is our achievement for the robot, agricultural robots. Now here is a rice plant farming, tillages, spraying using drones, planting, harvesting by the combine harvesters. Planting is developing by the NARO. This is National Research Institute of Japan. And also the harvesting robot is Kyoto University is developing here. But this is basically the almost same accuracies, less than 5 centimeter errors. The other thing is upland farmings. This is Hokkaido University's work. Fertilizing, seedling is possible, and then weeding and spraying also possible. Okay, this is not still there are no companies to sell this kind of the robot systems, weeding, spraying, without any damage to the crops because of high accuracies. And then another thing is that this robot can go to the field by itself. Therefore, it's not necessary to bring the robot tractor to the farm. The robot tractor go to the field by itself, and they work there, and complete it, and back to the bank. This is possible. But unfortunately, current public road traffic law, this is very important law in Japan. This is doesn't allow us to use robot like this. We cannot run, or unmanned tractor cannot run on the public road. This is the regulations. But technology can available. So, but the important thing is safety. Absolutely, definitely. So we are now, many companies also are developing very good sensors. And also our laboratory is also developing safe devices, safety sensors. We are developing, we use the omnidirection cameras. You are mounting the top of the roof. We construct stereo visions on the omnidirection cameras. This can cover 360 degrees. And also that we are now developing also that the laser scanners, laser scanner. We mounted laser scanner back and rear, front and rears, and then cover 360 degrees surrounding a robot. Each laser scanner is covered 270 degrees, but using 2 laser scanners, we can cover whole of them. And then also that we moving the back and forth. Okay, and then detect the 3D. So this is a demonstration. It's weeding. Robot is weeded. And then you can see someone get in the front of the vehicle, stop it, and make a run. even though the lateral side, lateral directions, recognize that by the sensors, and the rear too. And then also that, we are moving, shifting, up and downs. Therefore, even though small kids and the small animals can be detected by the but if crop is completely hidden by the peoples, it's very difficult to find it. It's impossible to find it. But if you can see very clearly the human, it's very easy to find out, and then stop it, make alarm. But anyway, and then also now in developing remote monitoring systems, we set up 2 monitors. One is live image around the robot. We set up that web cameras from the front, backward, right, and left. 4 cameras on it. And then the other monitor is a GIS-based monitors. So you can see, okay, now robot tractors go out from the bands, go to field, and then you can see live images is sent to the offices, and then we can see surrounding robot situation with the condition of the robot. And then another the monitors tell us current status and also where the robot is based on the GIS. If you have some problems happen, okay, we can immediately stop. And also that we can restart again. So you can see the robot is moving. Okay, this is we can recognize that robot working there. Another application we are developing is multi-robot tractors. As you know, Japan is a very tiny country. In main island, each field is very small. Okay, normally 30 which is 100 meters times by 30 meters. This is a common size. Farmers use small tractors, about 50 horsepower tractors. And then also, I come from the Hokkaido. Hokkaido is a little bit different. Our acreage is almost same with that German size, about 50 hectares, something like that. Therefore, farmers in Hokkaido use the big tractors. But now we are thinking is that a new concept of the robot tractors. We want to try to use the same size of tractors, small field from the big side to the large-scale field. So for instance, multi-small farmland is that each field is small. 50 horsepower robot tractor is working separately. Right hand is a large farm field. Usually people use big tractors instead of small tractors because of efficiencies. But we try to use the small tractors and then the multi-robots. Comprised of the small robots. And then small size machines are good for both safety and soil compactions. Then also we don't expect that each farmer has multiple robot tractors, small tractors. Our idea is to farmers borrow small robot tractors, each other's, and make a flexible and efficient work. This is our ideas. So robot tractor is 24 hours available. Therefore, sharing each other's, this is possible, I believe. This is ideas. Then, this one. Okay, Simon Blackman told me that they say soil compaction is becoming serious in the US and then Europe. Okay, this soil compaction make our soil pans. And then I heard that 80% of the kerosene for the cultivation in a year is for repair the soil conditions, break our soil pans. It's huge amount of energy is required. That is one, big tractor has a problem. The disadvantage of big tractors. And then another thing is climate change. This is Simon Blackman mentioned that. Big tractors cannot get in the field wet soil conditions. Sometimes now, climate change is caused that very heavy rains occurs. That is, farmers miss appropriate timing for harvest or farm works. This is very bad for the yield and then quality of the product. That is also that the big tractors cause make big problems. And then this is we are developing 2 machines working. Okay, but this is not like a human-associated robot I will show you before. This is both vehicle is completely unmanned, but human get in, ride on the one robot tractors. He's not holding the the steering wheel. He is holding a tablet PC. His job is that ensure safe operation of the robot. Okay, therefore, even night, it's very safe because of automatically run on the field. That is good thing. Oh, sorry. Okay, observation is human job. That system enable aged people, women, non-skilled people can operate robot because he doesn't need to operate, drive the tractors. Just only sitting there and then observe that the proper operation. So again, we are now developing a small robot tractors and then multiple robot systems. You can see the left hand is multiple small plants. This is we tested in the near Tokyo, downtown, the small field. Each robot tractor works separately, individually. Okay. The other thing is that Hokkaido, our field, 4 robot tractors work together. But these 2, this Honshu Island robot tractors and then our robot tractors same size, about 50 horsepower. But for the 4 robot work multiple robot systems is power, total power is that equivalent to the 200 horsepower because of 4 machines work together. Multi-robot system can be used for small farmland to a large farmland. This is the idea. So now here, you can see. The robot tractor is that, this is not individual. We can communicate each other, to make safe operations. So, formation. Oh, okay. Then, this is our Prime Minister is that introduced our technology last year. Prime Minister Abe is that he introduced our technology at 14th annual meeting of STS Forum. STS Forum is Science and Technology in Society forums. This is always held in the Kyoto cities. Last year, he introduced our technology. Please take a look.
Five years in a row, I have joined your annual meetings, and each time I've emerged even more optimistic about our future. I am a big believer in what science and technology can do to solve some of the structural problems we face. We must advance and benefit from science and technology. It is as simple as that. Take, for example, agriculture. In my country, farmers are aging, and their numbers are declining. But let's look at the positive side. One good example is robotics and what it can achieve. This August, on the farm in Hokkaido, there are 4 tractors running shoulder to shoulder. They were not normal machines. They were speaking with each other. In fact, those 4 tractors were in constant communication among themselves, collaborating with each other. These are automated self-driving tractors connected to each other. Their movement is accurate to within a mere inch or so. The precision of their actions will get even more striking as they will be linked to to the Japanese GPS in the future. Take a moment and have a look at the video to see how they run.
So this is our robotics. 4 robots work together, communicate each other.
How about that? Robot tractors could work rain or shine, day and night, even while the owner sleeps. And that is just one small piece of evidence that technology could make our agriculture all the more promising. You need worry about farmers again no more.
This is, he's a very good sales manager. But anyway, now he mentions that the Japanese GPS. We are using Japanese GPS as well. So we call Michibiki, Quiz-Zen satellite systems. Current GNSS cannot be used in any time, in any places in Japan, at least. Sometimes drop to the, float solutions and sometimes differential GPS, different solutions. That is, farmer need to be operate by himself. But, so therefore, low reliability due to limited number of satellite vehicles, and also acquisition collection signals for RTK has problems. QGSS, Michibiki, has been started in November 1 this year to develop satellite positioning services that can be used in stable way in all locations at all times. This system is compatible with GPS satellites and also that Galileo too, and then can be utilized with them in an integrated fashion. In this way, the satellite positioning services environment will be advanced dramatically. Michibiki QGSS can be used even in Asian Oceania region with longitudes close to the Japan. So its usage will be expanded to other countries in these regions as well. You can see the map there. This is QGS cover these areas. Therefore, Australia, China, Indonesia, Philippines, Malaysia, Thailand is that covered. The service is available. And then you can see the figure 8 is the orbit of the QGSS. So now this service is started this November 1 this year. So and then this is also the good introduction into the introducing our Michibikis. This is also that please take a look. Up the volume.
They've become an essential tool in many people's lives, but they can be off the mark. There's a new system being developed in Japan to create a higher standard for accuracy. NHK World's Akane Nakajima reports.
Fall brings the rice harvest to Hokkaido. Work is going smoothly, but there's no driver in sight. A satellite controls the harvester to centimeter accuracy. About 36,000 kilometers above Earth, the Michibiki satellite orbits as a part of Japan's first homegrown satellite positioning system. Most countries rely on the Global Positioning System, or GPS. But some factors cause GPS data to lose its accuracy on its journey to ground receivers. Two of these are the shift of the satellites out of their orbits and a delay in the signal caused by the ionosphere. They can be off by as much as 10 meters. The Michibiki system sends collection data and reduces the error to centimeters. Michibiki system achieved positioning at the level of accuracy. The key was producing the most accurate correction data as possible. This is the heart of the system at Japan Aerospace Exploration Agency. Correction data is being collected and sent to the Michibiki satellite. Unique algorithm is used to calculate factors that influence the GPS accuracy. Data is then produced to decrease the positioning errors. Improved accuracy creates new opportunities. One example is using robots for agricultural work. A group led by Hokkaido University professor Noboru Noguchi aims to become the world's first team to completely automate farming. GPS systems for farming are already used in places such as North America and Europe. Unlike this harvester with the Michibiki system, a driver has to be in the vehicle with the current system for safety and to turn the machine. The accuracy of the Michibiki system allows the vehicle to make turns by itself.
Okay, you know that this one already 2013. I mentioned that this year service started. So 5 years ago, okay, you know, we worked with the government. Therefore, we use that Michibikis during their development. Therefore, we tested using robot combine harvesters using Michibiki. But now this service is completely started. All of the people can use these systems. And then also we demonstrated, made performance demonstration in the Michibiki in other countries. One is Thailand, but the other one is Australia. So in the because of the Thailand and then Australia is covered Michibiki. So you can see, Thailand is also that it has challenges of the labor shortages. So that is cassava planting. This is normally two per person, the operator is needed or workers needed, but no operators. One person just only plant the cassavas. Okay, no drivers. That is, we demonstrated in Thailand last year using Michibiki. The other one is Australia. As you know, that Australia is a very huge agricultural land. Therefore, they are much interested in the unmanned robot tractors. We demonstrated machinery in the pre-show.
It's not science fiction anymore. It can do it, and it does it reliably. The tractor can do anything that a normal tractor can do. It can level the land, it can fertilise, it can weed spray, it can water. It has technology on the tractor itself, camera technology for collision avoidance and also obstacles.
The way it drives without a driver is using the software platform inside the tractor. They've integrated that with the GPS technology. So we put the run lines in that we use normally, and then the tractor operates autonomously, linking with the GPS system. The farmer could go to bed at 8 o'clock. That tractor could go round and round the field all night, come out, fuel it up the next morning, the job's done.
If we can achieve more productivity with less stress and less people, I suppose it's going to be a good thing.
So this is also that we tested 2 years ago. And then, Australia is also that they are very much interested in this kind of technologies here. And also that we tested the drones, monitoring the sugarcane growth, height, and also the NDVI, which is health of the sugarcane. We attach that in RG cameras, and then radars underneath of the drones, and then fly over there, and then make a map. The positioning is that the Michibiki QGSS used. So this is a result. We generate the map, height, and also that the NDVI map. This is very easy. And then now we are developing a kind of a harvesting robot using our robot tractors. The heavy crops like pumpkins, watermelons, these are very much laborious jobs. We already developed a mobile site, mobile tractors, multiple robots. We are now making a hand for the harvesting heavy crop, like pumpkins. Harvesting heavy crop is very laborious for farmers. The harvesting robot is able to perform selective harvesting, okay? And then without giving any damage to the crops. Target crops are pumpkins, watermelon, and cabbage, and so on. And then multiple robots used. Two robots, okay, in the front is that the container is there. And then the center robot is that it has a hand, and then harvest pumpkins, and then load it to the containers. This is, in the laboratories, we tested. Just only something. This is our goal. Now we are developing. The other robot we are developing is a smart farm robot. Actually, the current technology, our robot, is just only a simple task can be achieved. Okay? Just only go very much precisely, run. But they don't have any intelligence at all. Therefore, we want to add intelligence to the robot tractors, detecting disease, and also that the affection of the wet soil conditions, and also that the lack of the nitrogen. But putting intelligence in the robot is not good solutions, I believe, because of very much costly, and also the going up, the robot is become expensive. Therefore, we are now is that the intelligence is placed in the outside the robot. Crop status, weather pest, and then pest diseases is detected by the drones or whatever, and then through IoTs, go up, upload to the servers, and then AI, analyze the data, and then final result is sent to the robot. Robot is follow that decision. This is the ideas. Therefore, IoT, big data, AI is key technology for making an intelligent robot. This is what I'm developing. Then, in the last, I will show some kind of fun thing for using a robot. This is two robot tractors work together. What they are doing is that, drawing the pictures and writing text. So this field size is 400 meters by 200 meters. Two robot tractors work together to spend 12 hours, and then just only go downsing implement, tillage, and up in tillage. Tillage and tillage makes drawing or pictures. So now it's 12 hours, or even in night. So you can see, this is unfortunate, this is Japanese characters. But this, now, in Japan, drama, in terms of, dealing with the autonomous vehicle, robot tractor, is broadcasted. This is kind of advertising this dramas. Thus, person is a lead man lead of these dramas. And then this is character, letters is the drama, title of the dramas. 12 hours taken to make this one. But anyway, this is robot can do. Let me summarize. Japan government has been emphasizing development of smart agriculture technology to solve the problems of Japan agriculture. It expected that agriculture robots solved labor shortage of Japan agriculture. A robot tractor demonstration using QGS Michibiki was performed in Thailand and Australia. Smart robot is the essential for next generation agriculture, I believe. Thank you for listening.
Thank you. Thank you, Dr. Noguchi. We do have time for some questions for Dr. Noguchi. So anyone who has a question, yes.
You haven't mentioned, can you hear? Yeah, you haven't mentioned something which should be important in Japan, which is tea. Do you have any robotics for tea harvesting?
Tea harvesting. Okay, actually, that you're now developing. Maybe next year will be commercialized. Tea, yeah, that is tea harvest, kind of, harvesting tea. This is, but I'm saying is that Japanese tea. Yeah, Japanese tea is that now is developing, and then maybe come up soon, next year.
I do have a question for you. Where would you rank Japan in sort of on the global scale in terms of adoption of robotics within agriculture? Would you put Japan at the front edge of globally, or what would you say?
Actually, the Japanese now is manufacture agriculture major manufacturers start to sell only Japan, but they want to export this technology to the overseas. But problem here is guidelines, maybe a safety. Maybe the guideline is established, then maybe can start ready to sell, I think, commercialize. But very difficult, safe operation. I think, all countries, same situations. Not easy to sell without any guidelines, because of zero risk is not impossible. Always some risk exists for safe.
Please. Thomas Engel from John Deere. You have shown a lot of harvesters or machines from different brands. Are they all already commercially available, or when do they say they will really start to sell these machines?
Combine harvester, you mean? Combine harvesters?
Yeah,
okay.
For example, yeah.
Actually, the Kubota companies to plan to sell combine harvester, automatic combine harvester, but human getting the on board. But nothing to do, just only observing. This is the current situation, current technology. The close to the commercialization. But the amount is maybe take a time more.
Oh, up there.
Hello. Thanks for the good presentation. Question for you is, we saw the videos and the experience in Japan, outside of Japan, using these robots. So to have an idea is, for real farmers in Japan, are they using this technology? At what kind of percentage of use do you have today for this technology in Japan?
Actually, that this I told that the robot tractor is commercial this year. Therefore, not so many machine is not used in Japan so far. But farmers, in particular, has ones are large land. These are very much interested in this kind of robot technologies to reduce labor shortage, to solve the labor shortages of the agriculture sectors. But maybe problem here is still cost, actually. So this is a little bit expensive compared to the conventional tractors.
Any other questions for Dr. Noguchi? No? Okay, great. Well, I know you'll be around, so thank you very much, and we'll be able to answer questions during the break. Okay, thank you. Appreciate it. Okay, now through the wonders of technology, appropriate for a technology conference, our next presenter is going to join us virtually. This will be Professor Salah SUKKARIEH, who is Associate Dean, Industry and Innovation, and Professor of Robotics and Intelligent Systems at the University of Sydney in Australia. He's an international expert in research, development, and commercialization of robotic field systems. He's led a number of R&D projects in robotics and intelligent systems for logistics, commercial aviation, aerospace, education, environmental monitoring, agriculture, and mining, and also as consultant for industry. He was the Director of Research and Innovation at the Australian Centre for Field Robotics from 2007 to 2018, where he led the Strategic Research and Industry Engagement Program in the world's largest field robotics institute. Salah, welcome to FIRA.
Can you hear me? Is that okay? Can you hear me?
Yes, now we can hear you. Thank you.
Great. Yeah. Well, thank you, and sorry that I can't be there. It's getting close to our summer break here, and so everything's getting really, really busy, but I wish I could have been there. And so far, I've been watching it on YouTube, and it's looking really good.
Okay, thank you. And thank you for staying up with us. I think it's about 10 p.m. where you are, I believe. So.
That's right, 10 past 10. I just put the kids to bed and all alone now. So.
Okay, perfect. Okay, we're going to begin by showing Salah's presentation through video, and then when that's completed, then we'll do a Q&A here, right here in the auditorium.
Ladies and gentlemen, good afternoon. Firstly, I'd like to thank the organisers for the invitation, and secondly, I'd like to apologise for not being there in person. This is nearing our summer holidays and all our projects come to an end now, so it becomes a very, very busy time for us here. But I do hope that this presentation will deliver the message as if I was there in person. The objective of the presentation is to talk to you about some of the work that we're doing in field robotics and intelligent field systems and how it's being applied in Australian agriculture, and hopefully from that some of the lessons that we've been learning as well. For a little bit of background into who we are and what we do, I mean, Australia is a very, very large place. If you compare it, this is the true size of Australia relative to Europe, so it gives you some context of the size of the country. But there's only 24, 25 million people, and most of them live around the east coast of Australia. So the population is probably the size of London or Paris, but it has the same landscape, or land size, I should say, to that of Europe. If you look at the agriculture of Australia and what it comprises of, you'll see that we have quite a large variety of activity that's going on. In particular, and I'll just use my arrow here so you can see. In particular, so you can see the green areas here, which is around probably dairy, as well as a lot of horticulture work as well. That space is between there. The light grey here is representing the beef industry, which is probably one of our largest exporting items. The dark green also representing the wheat, for example, a lot of the cropping activity that's happening. So it gives you some perspective of where the agriculture is and what the agriculture looks like. So it pretty much branches all around Australia, except for the really extreme climates, the desert regions, as well as the extreme north where the tropical regions are, rainforest areas. And then if you look at the export activity that Australia goes through, you can see again a breakdown of some of the main activities, so meat and live animals, which is one of the biggest areas that we take out, as well as grains and oilseeds of the cropping activity. And there's a fair bit of horticulture as well as dairy products as well. So it gives you a perspective of the area, also the activity space. And what's important, I guess, also is that out of all the production that we go through, almost 80% of the production is exported. So we can feed the population here, and then 80% of the thing that gets exported around the world. And then if you look at the kind of size of the average Australian farm, you'll see that it probably has on the largest per hectare in terms of average farm sizes, even bigger than what you might find in North or South America. And that talks to very much the population versus land size. The Australian population density is about 2 people per square kilometre. So hopefully that gives you a bit of an overview of what Australian agriculture is like. But Australian farmers pretty much face the same challenges as any farmers anywhere around the world. We have an ageing farmer population. We have no real succession plan. Most kids go off into the city and don't come back. There's low labour availability. We have probably the highest labour costs and probably the highest minimum wage level in the world. And so we have a very high labour cost with large area sizes and low labour availability. So it's quite a significant undertaking that we have to do within agriculture when it comes to labour. Climate change is having a big impact on us. It's changing the way pests and diseases work in that environment. We're getting significant chemical resistance, and obviously there's water availability, especially in a country like Australia, and so on and so forth. There's many aspects there that we're all familiar with and that we all understand. So in context, when you start to think about what the challenges are on an Australian farm, low labour, large land sizes, climate change impact, and all of these things have a desire. So when you see it, the desire then for robotics is quite strong. And in fact, Australia has a very important history when it comes to robotics. We have the largest automation programs in the world. For example, most of our mining activity is automated. Most of our stevedoring activity, so what works on the berths, are automated. And also, if you look at our logistics, we have quite significant logistics, and a lot of the operations, especially when it comes to planning, is automated as well. So agriculture is just really the next primary industry that we're looking at that looks at automation. So I'm just going to go through some examples and go through what we've been doing. The first example that I want to do is tree crops. It was one of the first projects that we had.
This is just an off-the-shelf platform in terms of what's down the bottom, but you'll see here that what we've done is we've added a lot of different sensors, and the whole idea was to have an automated platform that can go up and down tree rows, and then we could collect all this data information and start to determine what works and what doesn't work for different types of tree implementations. So for example, this is just a typical process that we would go through in real time. The laser unit here is able to detect individual trees, along with some algorithms to detect individual trees, as well as what's going on underneath in the soil, so we can measure soil properties and soil parameters as well. And then when you couple that with vision data and with other sensory data, you start to be able to remove and identify individual features within the tree, such as individual flowers, individual fruit, and so forth. As an example here, this is a mango plantation, and we've been able to, using techniques in SLAM algorithms, simultaneous localization and mapping, as well as laser data, we can identify each individual fruit as we're going through, and based on volume size of the individual tree, we can start to have an estimate of how much fruit there might be on there. And we're getting, when we compare this to different types of trees, so we've done almonds, mangoes, bananas, avocados, and so forth, we actually get some very good accuracy, almost above 95% accuracy in the results that we have. So that was an example in tree crops. The other ones I want to show you is in row crops, and in particular in horticulture. This is a particular platform that we built. We call it Ripper. The whole idea was to develop a solar electric robot that could operate for 24 hours, 7 days a week. And the whole idea was that you could demonstrate the capability of the robot going, and it has a number of different sensors underneath that looks down onto the crops, and as the robot goes up and down the rows, we can then start to extract a number of pieces of information from there. So as an example, this is on a lettuce farm. This is Ripper going up and down the rows autonomously. You'll see now that it's got the collection of data that it has through there. As it's coming up through here, we use machine learning techniques, as you would expect, to be able to detect individual plants and start to look at the size of the plant, and hence from that deduce the crop health potentially, or vigor. This is looking at crop yield information, so can you start to envelop the plant with different types of models to try and understand crop yield. If you can detect the weed, then you can, so if you can detect the plant, you can also detect the weed, and sometimes when the weeds are really small, you can come along and just be able to mechanically remove those weeds as you're going through. So this is just showing you some of the activity. We can also identify each individual plant and target and spray plants. So here is on a cornfield, just targeting each individual plant and spraying the right amount of fertilizer, for example, on each individual plant as we go through. So it gives us that capability. And also we can do things such as measuring water conductivity. So in this particular case, measuring water just next to a plant. So what you have now is this robot that can operate 24 hours, 7 days a week. It can weed, it can spray, it can measure water, it can look at crop health, crop intelligence, and you start to build up all the data, and you can start to look at building up maps of information, crop health, crop status. We've also used the same robot in say in the apple industry in this particular case. Here we've got the same robot going up and down, and you can just see this white sensor payload that's over here, and we can detect and identify each individual apple as we're going through. And what you'll see next is also the targeted spraying. So here we're targeting and spraying each individual apple. Now, this is just us as roboticists coming along and making and building different tools, and from those tools being able to deduce, being able to demonstrate different types of activity, and from there the farmers can deduce what's important, what's not important. The other area that I wanted to talk about was grazing livestock, and as I mentioned before, it's quite an extensive industry. This is one of our first demonstrations with a robot that could go through undulating terrain of different types, being able to go over logs and rocks, and this is all about looking at very, very difficult terrains. This was one of our first implementations about herding, and we thought, you know, how does a farmer now move animals from one spot to another? And so we looked at what would happen when the robot moved amongst the animal herd and how it would behave, and just trying to see what the animals will do. And as you can imagine, when the animals, when they see this robot, they kind of get a bit scared, and they want to move away from the robot. They don't quite like it, and it becomes very, very hard. If you wanted to move an animal from one location to another location, it becomes very, very hard and very difficult to be able to do something like that. They just go everywhere. But after a while, what we learned was that if we keep the robot with the farmer all the time, then eventually the animals get used to the robot, and you don't actually need to push them anywhere. And in fact, what you can do is just move them. So this is the second generation process. Eventually the animals got used to the robot, and then we can move from one location to another, and we can actually start to move the animals around. And that becomes quite an important achievement, because now what you can do is you can measure pasture quality, and with pasture quality you can move the animals from good pasture to better pasture and not have them overgraze. And this is what you can do then is as the animals are moving around you, you can start to detect what's going on with the animals, and how they're moving. You can measure their position, their velocity, where they're grazing, where they're spending most of their time, and then you can start to look at animal-pasture relationships and even maybe animal health. The other thing that's important in grazing livestock is also weeding. So this is the robot detecting weeds in real time, and being able to determine where there's a weed and where there's native vegetation, and then it positions itself amongst the weeds, and then it can actually come along and spray the weeds with the right amount of herbicide or pesticide at that point. So I was just showing you some different aspects around many of the different growers, but for most robotics it will happen for large scale farms. And what we've also tried to look at is what happens with smallholder farmers. Can we actually develop technologies at lower cost that will work for smallholder farmers? So this is one of our first implementations where we took we designed a die wheel, so a two-wheeled platform that could come along and be able to build up very easily remove, put together, put it into the back of a vehicle. You can see the sensor payload right in the middle there, but you can just kind of move it along, put it into the back of a vehicle, move it from one farm to another farm, and then start to collect some crop information from there, as you can see here. And even though it wobbles, as you see there, all the algorithms, the software algorithms take care of it. We can actually start to do the crop intelligence from there. We took it to a whole range of farmers and demonstrated different types of capabilities for it. So this is, for example, the robot going up and down the rows, and it can detect individual plants, and from those individual plants we can then come along and look at spraying individual plants, as well as being able to look at different seeding technologies as well. So it gives us a capability that we can actually start to look at. We took that robot to Fiji, Samoa, and also to Indonesia. This was part of some trials that we got funding from the Australian government to look at developing countries. So it's the same type of robot. You don't need all these people. You can actually just winch the robot down as it's going through. And we did the same thing where we took it to these different farms and we demonstrated the capability of it, being able to detect individual plants, and also do things such as spraying and weeding technologies. And what we found is, again, even going to developing countries, was that farmers there have the same constraints that the farmers in Australia do, just at a lower cost margin. And so being able to develop these technologies to be able to work for this lower end, it becomes really important. And a lot of tree crop activity happens in the Pacific Islands. So we also demonstrated how this robot could be used in a tree crop application using the same technologies that I mentioned before. So here it is, just coming along and doing automated spraying along the tree row, being able to detect how to move along the tree row and do so autonomously, as well as being able to detect individual fruit. So this is a nectarine orchard. Being able to detect individual fruit as well becomes important, and being able to determine from there how much to spray and where to spray. So that gives you hopefully a rundown of where we are in Australia and the Australian context, and hopefully that gives you a perspective of the types of activities that we're looking at. We have very, very large farms, as I mentioned to you earlier on in the presentation, and hence robotic systems for that, as well as smallholder farmers. And in the country like Australia, where a lot of it's exporting, the real benefit that robotics is going to provide is the ability to be able to increase yield, as well as decrease variability, and be able to deal with the large-scale export rates that we go through. So I thank you for your time, and I'm open up for any questions.
Great, thank you, Salah. Salah, it seems as if Australia is a really good lab for automation. You know, for almost a global sort of model. You know, you're in horticulture crops, you're in row crops. There's a lot of a history of automation. Are there any sort of extractable lessons that you would say from Australia being on the cutting edge that could be applied here in France or in Europe or in North America?
Yeah, I think we've always had a very high international profile and on the trade market quite competitive. It doesn't really matter whether it's in mining or logistics or whatever it might be in agriculture, is no different. So Australia's always had a very high tendency to accept robotics and automation in different industries. What we find with the farming groups and the organisations is they also are very, very amenable to adopting this technology very quickly. It's the same thing that I've been hearing all morning, though. It's about how do you reduce the cost and how do you make it reliable, and doing those two things simultaneously can be quite difficult. But I think the other interesting aspect that I see in the Australian context that I haven't seen around the world yet is there's a much more freer ability to kind of think beyond the robot. So we're actually starting to talk now about what does the farm in 2050 look like? How would you change plant architectures? How would you change tree architectures or farm architectures? What do you need to do around communications and systems to allow autonomous farms to happen in the future? So moving beyond just the robotic system.
Great, okay. Questions from the audience? We have a quiet group today.
Hello. Paul Brooks from the UK. Have you done any research looking at using electricity or steam for weeding rather than just chemicals?
Yeah, so I've actually most of our weeding work is non-chemical weeding. We've done that from day one. The focus has always been about how we're using robotics and automation now. So how do we do non-chemical weeding? We've done mechanical systems. We're currently looking at laser systems. We've looked at electrician, and we have looked at steam, and it really comes down to the amount of energy that you want to impart on the system and how big the land is. So there's this trade-off between, in our case, if we're trying to build small, low-cost robots that are running off electricity, battery-operated robots, then you're limited to what type of technology you can use, except if you start to look at tractors. And there's been some work, for example, in other universities around using radars, or microwaves, sorry, I should say, to be able to also nuke basically weeds. So there's been a big drive around that space, and it depends on the size of the farm, it depends on the robotic system. But yes, we have been looking at a number of different non-chemical weeding techniques.
Do you have any comments on which are the most energy efficient out of those non-chemical ones, apart from mechanical weeding, of course?
Apart from mechanical weeding, it's well, I mean, laser weeding seems to work, but you have to actually move quite slowly. You have to have you have to kind of maintain a certain time on target. If you're looking beyond the mechanical, microwave weeding seems to have quite a significant potential there. The startup startup energy cost seems to be quite significant, but once you kind of start it up, the runtime energy cost is low, so that seems to be working well. But mechanical weeding still seems to be the trumps in terms of being able to do something robustly that can work for long periods of time on farm, and also at the same time have that energy balance. And it's a complex multi-objective optimization problem that you need to look at.
Thank you.
Welcome. Great. Yes, over here.
Jose Miguel from Chile. 3 questions for you. First, for how long have you been working on this project? How many people are involved? And then those products are still under developing or are commercial products?
Okay, so how long? I started working in drones in agriculture, and that would have been about 18 years ago. We then moved into ground robotics about 10 years ago, when we started to look at more implementations on a farm. The size of the group at the moment now is about 25 people, 30 people almost, split almost half between researchers and engineers. And as for commercialization, we've just gone through now a round of venture capital funds, and the technology is now being spun out and put into operation on some farms.
Other questions? So you have been watching the video. Any observations that you've had from what you've heard? And also, have you come across some of the logistical issues that have been mentioned, getting robotic units from field to field and theft in the field?
Yeah, so no, I think watching the discussions that have happened already, I think we have very similar concerns in Australia. Anything from the cost and the robustness of the technology on farm, education is also an important element. Australia, as I showed right at the beginning, I tried to show the context of how big the country is. The closest farm that I have to my university is, our closest good operational farm to my university is a 5-hour drive. So that kind of gives you some kind of context to the logistics that we have to deal with as well. But we're a believer that the technology will help that. 3D printing, I think, will go a long way to kind of solve a lot of the problems that we're thinking from a logistics perspective. The concerns that I heard being raised earlier, I think, are kind of actually, I mean, as they say, a feature. The fact that you can actually take this technology out into farms and almost democratize agronomy. I mean, that's the big thing for me at the moment now, is the fact that this technology will actually digitize agronomy and provide farmers with that 24/7 agronomy service they could before, which generally means that we'll probably end up seeing decentralized food supply chains and democratization of agronomy. And I think that has a huge uplift in agriculture. So what you see as a problem can actually be turned into an advantage, and we're seeing that in the Australian context. I have a major program now with the Australian government to teach rural schools about robotics, and we actually take a lot of our robots onto schools and teach the next generation of growers about robotics, and that's something that's important, which is how much time do you spend trying to cater for robotics in the Australian context anyway, for a 55-year-old farmer, a 60-year-old farmer, versus waiting a little bit and actually teaching the next generation of growers, the 20-year-olds, who are very much used to this technology and how it works. And there's that balancing act when you start to look at, when you should introduce that technology into the field.
Mm-hmm. Yes.
Hi, this is Jaisama from India here. From a cost perspective, what seems to be the biggest roadblock to bring prices down? Is it the wheels? Is it the onboard compute? Or is it just purely you're trying to amortize the R&D that's been spent for several years?
I think that's a good question. I think the R&D is significant. It's a huge cost when you start to think. If I had to add up over the 10 years the amount of work and knowledge that had to be gained, it's quite expensive. But once you've got the IP and it goes out, then the manufacturing cost of the unit drops down quite significantly. The cost relationship comes down to, and this was touched on a little bit by the previous talk, is around precision and risk. So those two things, when they come together, you start to work. The sensor cost actually is what takes up the largest percentage of it. If I wanted 2 centimeter accuracy GPS continuously, then that's $10,000, 10,000 AUD dollars. I can build a whole robot for that cost without the sensor. If I'm looking at obstacle detection that has to work in a dusty environment, as well as at nighttime, as well as in fog, then I'm looking at another $5,000, $10,000 sensor unit. So all of a sudden now, half my robot cost is just on 2 or 3 sensors. So it's a relationship between accuracy and risk. That's usually where you find the costs getting imparted onto the platforms. And so one way of getting around that is how do you mitigate that through the environment itself? How can you restructure the environment to make it easier for automation to come in? And we've seen in certain situations that being able to close off paddocks and being able to level everything quite nicely beforehand, you can reduce your sensoring costs by almost 2/3, and that gives you a much better output. So the mechanics, initially 1 unit cost is expensive. If you start to say what's 100 units, it becomes really cheap. What you want to do maybe is work with the automobile industry, where they work with trying to deliver 1 million sensors, 1 million radar sensors, for example, and each radar sensor can't be more than $2. So if you can start to tap into that space, then you start to reduce the cost of your sensoring systems as well.
Other questions? You know, Salah, you bring up an interesting point. And about, automation, we talked about tractors, and it seems as if that was more readily adoptable because it was used in very large row crop operations, whereas a lot of robotics probably have more immediate applications in the more labor-intensive, the specialty crops, the produce crops. And you think that might be hindering kind of reaching economies of scale with robotics?
Yeah, it's a good point. I think broadacre crops are easy. You have flat land, you have open sky. And so you can take current systems and automate them quite easily, or you can build very simple systems. But when you start to talk about difficult terrain, or even just to say, how do I build a robotic system that will deal with 80% of the growers that are out there, then all of a sudden you have to start to build more complex systems. And you have to do that and reduce the cost at the same time. So I think we look at it from a robotics perspective, and so there's lots of algorithms that have been developed in the robotics literature that don't rely on GPS, for example, and it can do very simple obstacle detection systems and can do very simple control algorithms that work very effectively on difficult terrain, as opposed to saying, I've got a tractor and I'll just add a GPS unit and go from there. So it's a battle almost between, it's like a David and Goliath kind of battle almost in that space. I think as, but you're seeing trends and you've got the big players who have a certain level of infrastructure in building tractors and their distribution channels. It makes it easier for them to just stick to those types of models and put GPS and whatever it might be to make them automated. But then you've got the startup world, which seems to be kind of tapping into the intelligent autonomous car market, for example, and all the sensors and algorithms that come out of your Google car can be thrown onto these little bots and off you go from there.
Okay, great. If we have time for one more question, if anyone has one, if not, anybody? Okay, well, Salah, thank you very much for joining us, and sorry you couldn't be here at FIRA, and again, thanks for joining, and we'll let you go to bed.
Pleasure, thank you all.
Okay, bye now. Our last presenter not only is not joining us virtually, he's actually already here on the stage, and he is going to be talking about how an international group met the challenge of agricultural robotics. He is Maurice GOHLKE, who's a robotics engineer at the Bosch Deepfield robotics startup in Germany, who focuses on robotics software and machine learning for plant classification. A graduate of INSA Lyon and Georgia Tech, he works on boxwood recognition for the Bonorab robot platform and the automation of field tests with the 4D phenotyping robot. The team is now developing standalone machines to improve the management of conventional and organic weeds, with its first solutions to be provided to organics sugar beet growers. Please welcome Maurice.
Right, so I want to say a couple of things about what we think we can change with new technologies in terms of weed control. So we're from Bosch, from Deepfield Robotics. So we've been doing a lot of weeding robots. Actually, Bosch has been doing agricultural robots for 10 years. And if you look at this, this image, the oldest robot is actually the most complex looking, which is the Bonorab V3 in the center. And that was a platform for different types of tools, mostly used in research. So we have different universities that use this robot to try different tasks for agriculture. And then the goal is to actually go from this research platform to a real product for farmers. And basically what you see on the lower left is this Weedmobile. This is something we have shown at the Agritechnica in 2015. So this is a robot that recognizes plants and then uses a stamping tool to stamp through the stem of a plant and kill it. And this was already less complex than the Bonorab and going more towards something that can be used by farmers. Something else that we did is this 4D scan robot. So this is a robot for field trials. So say you're a company, you make trials, and you want to compare different genetics, for example, on a field. So you use this robot to scan the plots and get information about the number of plants, types of weeds, the size of the plants, information like that. And then we had this fancy platform on the bottom right to basically visualize what's happening on those field trials. Okay. So based on this, going from this more complex, more researchy robot to something used by farmers, I want to show you what we did in 2018. Okay, so this is a sugar beet field close to Stuttgart, where we're based in Germany. And sugar beets, like other crops, you have to protect the crop from weeds. And basically the main method used is to use herbicides, which has a lot of restrictions and trying to use less herbicides. So few farmers in sugar beets, they use hose to care about the weeds in the interrow. And the actual method that was used a long time ago and is used in organic farming for sugar beets is basically manual hoeing. So the question is, what if we did the same thing that the human does when he hoes the field manually, but with a robot? So just like the human walks over the field, the robot's basically driving over the field, and we use our eyes to see the plants, and this robot uses this camera system to see plants. And then we use our brain to make the classification between different types of plants and then plan how to use our arms to kill the weeds. And we do this with artificial intelligence, so deep neural nets. And then we have this chopper tool that is moved towards the weeds and kills them by chopping them. So here you can see it driving during the day and into the night. So really the main thing that we have is this technology that we have been focusing on, which basically can detect plants in different fields, different types of weeds. And our robot is really a platform that we have, so we can use our technology on the fields. You can see them working together. Okay, so how does this work? Okay. So basically we have a camera system, a camera which is very close to the ground. This is very important if you want to have good resolution and all the details of the plants, so you can recognize the small plants, like plants that are really the size of my fingernail. And then those plants you can see on the image, they look very green, but that's not because our plants are that green on our fields. It's because we replace the green channel with a near-infrared channel. So we use a multispectral camera to get better images of plants and make a better classification. We also use an active lighting system, so we're independent of the sunlight. So then afterwards, we use some deep neural nets to do a classification of plants. And we do this on a pixel basis. So this is not big plant versus small plant or taking blobs and classifying blobs. This is really for each pixel we say what type of weed it is. And it's also not only sugar beet or weed, but different types of weeds. And with this we can deal with overlapping plants. So if you have several types of weeds together or weeds which are overlapping with sugar beets, we can still classify them. And then once you know which one is the crop plant and which one is the wheat plant, you plan your tool so it reaches the weeds and spares out the beets. And for this, we tried many different tools. And this is not actually the main thing that we focus on. The main thing that we focus on is really the recognition. But here we really wanted to show one example of something that works well to kill the weeds in the intra-row and weeds that are very close to crop plants. So, as I've said several times, really the focus is the machine learning part. And for this, you need a lot of data. And you need very varied data. So just like a kid would learn to distinguish between different types of plants, we have to teach our classifier to distinguish between different types of weeds. And for this, we have, the last 4 years, recorded a lot of data. That's data with different types of weeds on different fields. We have over 4.3 million labeled images. And also, plants don't look the same during different times of the day. So we have images in the night, in the morning, at noon, and so on. Again, you see, again, on the right, some of the main features. So dealing with very small plants, overlapping plants, being independent of sunlight through active lights, and using this multispectral camera. So this is a technology that we're using on the robot, but we see that for different types of fields, different use cases, different crops, you might need different types of tools. So basically what we're doing now is we're continuing to use our robots to treat our fields and to enhance our technology, but at the same time we're also working with integrators. And those integrators can use our system to do this plant classification and then actually get this technology, and that's what we really want, is actually to get this technology to the farmers so we can use it to do different types of more modern weed control. This can be mechanical, but this can be also chemical with some savings in chemicals. That's it. Thank you.
Thank you, Maurice. Any questions for Maurice?
Okay, thank you. Denis Mazerolles from the Tea-Grown in Europe Association. Can you elaborate a little more on the purpose of using multispectral imaging? Is it also useful to discriminate the weeds from the plants you want to keep?
So you see it very well if you use an RGB camera, or so for us it's just one additional wavelength that we use, so this near infrared, and you can see that let alone to make simple vegetation segmentation, so what is crop and what is background, it's already much easier just with using this additional channel. So we're actually also looking into using just normal RGB cameras, but it's definitely easier with a multispectral camera.
Any other questions? If not, well, thank you very much, Maurice. Appreciate it. Thank you.